Please tell me, what is it, a Wilberforce pendulum?
The Wilberforce pendulum is an example of a mechanical oscillator. It consists of a mass suspended by a long spring and which tends to turn and oscillate. It was invented in 1894 by the British physicist Lionel Robert Wilberforce. But physics was not his only passion, there was also the diabolo. It is even said that one day he brought his diabolo to one of his lectures in order to illustrate the principles of dynamics and...
Stop! You're digressing.
Sorry. To be more precise, the Wilberforce pendulum is a coupled mechanical oscillator composed of a mass suspended to a spring with no contiguous convolutions and free to turn around the vertical axis of the system, creating a twist effect. The pendulum has two main motions, the translation and the rotation, and if you look carefully, when one motion is at its peak, the other one is almost non-existent.
Wait, what? How is that?
It's all about energy. We can consider that the energy is divided between the longitudinal movement and the rotation. Thanks to the conservation of the global energy of the system, when the energy used to spin the pendulum increases, there's less energy available for the vertical oscillations, which lessen, and vice versa. Thus, those two movements are coupled and can't reach their peak at the same time.
And I suppose that you're again going to tell me that all this is ruled by equations?
Of course, it's physics. First, we have to acknowledge the form of the potential energy of coupling. There is a clear link between the rotation by the angle theta and the translation, set for us. The other potential energy comes from the spring. It's the elastic potential energy. K is the spring constant. Now that we have found all the potential energies, we can proceed to the fundamental principle of dynamics. The mass times the second derivative of z equals the force due to the spring, plus the term that follows the differentiation by z of the potential energy of coupling. The other equation is given by the angular momentum theorem. The moment of inertia times the second derivative of theta equals the torque of the spring, plus the force due to the derivation by theta of the potential energy of coupling. K prime is the torsion spring constant, which expresses the tendency of the system to resist to torsion. We finally have a system of equations. We solve it, and we get the expression of z and theta. Now, let's see the graphs. Everyone loves graphs, don't they?
Of course.
We have the horizontal time axis, the vertical theta and z axis. According to the theoretical results, the curve should be like this. The coupling of sine and cosine draws a periodical curve. We can really notice that when the amplitude of one of the curves is at its maximum, the other one is at its minimum, and vice versa. Next step, we draw the curves obtained thanks to our prototype.
I'm sorry to say, they are not exactly the same.
I very much agree. There are two types of mistakes. On the one hand, our prototype is far from flawless. The link between the mass and the spring is not perfect, and the constants of the system are not perfectly known. On the other hand, approximations have been made to solve the equations. Indeed, some phenomena like the air friction have been overlooked.
Physics dislike cheap tomato cans.
One important thing to know is that there exist two particular modes of oscillation, which we chose to name symmetric and antisymmetric modes. The symmetric mode follows the natural way the spring turns, and in the antisymmetric mode, the spring turns the other way. They can be seen by imposing at the beginning of the experience particular initial conditions. These two modes are the normal modes of our system. From a mathematical point of view, they are the most simple modes the pendulum can have. All the other modes are linear combinations, overlays of those two particular modes. The Wilberforce phenomenon is actually a never-ending battle between those two oscillation modes. Here we are! Finally, a Wilberforce pendulum is all this, and don't forget,